We want to talk about germ of a function. So say our function is y equals to 0. So that is our x-axis. And we want to talk about the germ of this function at a particular point. So say the point we pick up is origin. So our point is origin. So what is the germ of y equals to 0 at the origin? So it is set of all functions which agree with the x-axis in the neighborhood of 0. So the functions would look like this. So this function agrees in the neighborhood of 0. Say another function, this again agrees in the neighborhood of 0 with the x-axis. Notice that y equals to x is also a function which goes through origin. So although at point 0 it agrees with the x-axis, it does not agree in any neighborhood of 0. It just agrees at one point. So this is not in the germ. So y equals to x is not in the germ of y equals to 0. Now you could talk about another function. So say now we talk about another function, say x minus 2. So y equals to x minus 2. Now this function we have to talk about its germ. So we will again talk about its germ in the neighborhood of 0. So all those functions which agree with this function in the neighborhood of 0. So for this function the neighborhood is right here. So say there is another function like this. So this agrees in the neighborhood. So this is in the same germ. So now let us come to the definition. So a germ of a continuous function f at a point P is a small piece or shred of a function in the open neighborhood U of P. So here we were talking about open neighborhood U of 0. So our point P was 0. So germ at P is f comma u, so function and the neighborhood u of point P. Modulo out with the equivalence relation. So two functions f and g are equivalent if they both agree on some smaller neighborhood. So on a smaller neighborhood w, which lies both in u and v. So two functions have to agree in some neighborhood. So there is some tube on which they agree. So you can see y equals to x agrees exactly at point 0, but not in any tube or any neighborhood around. So that is why it is not in the germ of y equals to 0. So there are many such germs. So we saw another germ y equals to x minus 2. There could be another germ of a function right here. Another germ could be right here. So all these germs are corresponding to point 0. So you have this neighborhood and then corresponding to that see what functions agree here, what functions agree here. So you can take all these germs. So the set of all these germs is called the stock. So this line becomes the stock. Now these germs are just functions, so you can add them and multiply them, and the stock becomes a ring. Now this stock is now a ring. Now this ring has a maximal ideal. And what is the maximal ideal? It is precisely the germs vanishing at the point P. So that is, these are all functions. If you put in 0 in them, you will get some number. Now if that number is 0, that means that function lies in the maximal ideal. So let us see it concretely. So say if we denote by this C of u as sheaf of continuous functions f going to complex numbers, and C of p as the corresponding stock at p equals to u, you get something like this. The C of p is your ring. This ring has this maximal ideal m of p, that is the functions which vanish at p. So you evaluate at p. So obviously you take any function f and you put in the points. What you're going to get is a complex number. So you get a short exact sequence like this. So say p is 1, then x minus 1 goes to 0. Because you put in 1, you go to 0, you evaluate at point P. So x minus 1 lies in the maximal ideal. This is the inclusion. What about x plus 2? X plus 2 goes to 3, and so on. Now, in category theoretic terms, what we have just described right here, this is nothing but direct limit. So direct limit is also called co-limit. It is also called injective limit at the point P. So let f be the pre-sheaf on the space x, then stock at point P is f of p, this f subscript p, take the direct limit over all sets u, and p is contained in u. So this is nothing but right here, germ at particular point, and then you take all the germs, because f of u consists of different sections. So corresponding to each section you find the germ. And so you have section 1, section 2. Take all these sections and their germs, you get a stock. So finding the germ is the process of this direct limit, which is precisely this right here. So let us give some concrete examples. So the first example is O of u, let it be the sheaf of holomorphic functions on some u. We want to find the stock of this sheaf at say some point P. So P lies within u. So for this you have to talk about functions. So say you have two functions, f which acts on u, lands in C, another g which acts on v and lands in complex number c. So say f and g are both holomorphic and point P lies within u and within v. So then f and g, these two functions agree on some smaller set w which lies within both u and v if and only if both f and g have the same Taylor expansion in the neighborhood of P. So if they have the same Taylor expansion, that means they have the same germ. So this is it. This is your stock at point P. So you can have as many functions as possible here, because you can just keep on feeding AIs and get different functions every time. And because of this here, because of this Taylor expansion will agree if both the functions agree in this W. So you have the germs. So this is a very good example because you can see everything kind of comes from here. So you can start with this example and then go back here. So start from here, this example, this fact from complex analysis, and go back here. Now in algebraic geometry we have this V as a affine variety. So associated to V we have this ring K of V, and you have some point on V. So what is the stock at point P? It is just functions like G by F, where both F and G lie in this ring K of V. And obviously for this to make sense, the denominator is non-zero. Now it also has a maximal ideal, and the maximal ideal is contained within the ring. So it satisfies all these conditions, plus G of P is 0. So obviously same thing here. It is a set of germs which vanish at point P. So thinking in terms of stocks is very, very important. So this will become clear now. So say you have a skyscraper pre-sheaf of 2 points. So you have 2 points. On each of the points you have a ring sitting of integers. So say you have integers here, and you also have integers right here. So now here, say you have a section here. Section takes on value 2 here, and there is another section taking value 3 here. So there is no way you can glue them, because there is no integer which will become 2 here and then jump to 3 here. So what is the easiest possible way to make this pre-sheaf into a sheaf? So you do the minimal amount of work. You take the disjoint union. You take the section as 2, 3. So you restrict it on this point P1, you get 2. You restrict on this point here, P2, you get 3. Now you can see that this looks like a stalk at 2 points, P1 and P2. And this is the general procedure. In fact, every sheaf can be thought of as a collection of stalks. But first, we will go through a procedure of making a pre-sheaf into a sheaf, and that involves operation with stalks. So we can make any pre-sheaf into a sheaf by a process called sheafification. So first you start with a set of functions. So this f goes from u to disjoint union of the stalks. So what is basically happening, you're taking the function f, you're evaluating it at point p. So this f of p we are writing as f subscript p. So you have all this disjoint union. So f gets mapped to all these points. So fp1, fp2, so on. Well, p1, p2, p3 all lie in u. So you have this. So this will be called as sheafification and subject to certain conditions. So this you write as f superscript this dagger for the sheafification process. So what is the condition? So the condition is right here. We will draw it. So say you start with a point in some neighborhood u. So you have this point P, and this obviously lies in some neighborhood, say u. So obviously you have f of u, which is a ring, and this f of u has some, say, section f here. Now you take a smaller neighborhood. So say you have taken a smaller neighborhood v. Corresponding to it you have another ring, say f of v. Now this f should have some correspondence to some element here. So say that element here is s. So obviously you're shrinking here. You have to have the gluing condition and the uniqueness condition hold. So there has to be some correspondence. So in particular, since we are talking about every point, so you pick up a point, say y here, this f evaluated at y should be same as s y right here. And that's what the condition is. Basically, we have a pre-sheaf here. We have to add two conditions to it. So the conditions we have to add to it are uniqueness and gluing, and they kind of merge together in this notion of a germ. So notice that if we are forcing them together in small neighborhoods, that means we have some kind of equivalence of germs. Now we will write it down what we have just drawn. So for all points P in U, there is a neighborhood V lying in U of P. So V lies in U, and V also contains P, and a section S of f of V, the section S of f of V, such that this holds. This condition holds for all these points y in V. Now we have rigged this definition. So this definition has been rigged or made up precisely because this should satisfy the gluing and uniqueness condition. So that for a sheaf at the level of stalks we have this. You take a sheaf and then you sheafify it. At the level of stalks it should be the same. In fact, you can say more. These two sheafs are isomorphic. Now this follows from universal property, which you can see in Hartshorne. So the reason why we talked about sheafification is that it makes sense always to think in terms of stalks, because these stalks have a concrete description. These sets u and v keep varying, but these stalks are like just at a point. So one needs to understand what is happening at stalks. So the idea of this entire lecture was, from my point of view, that you basically start everything from here. You think of sheaf as a collection of stalks which have these certain germ conditions. So you have these germs which are holding together these stalks. So the idea is this, that before thinking of sheaves, you think of on some space what are you putting at individual points? What kind of rings are you putting at individual points? So these rings are called stalks. So you start with stalks, then you put some gluing conditions on them, which essentially are germs, and then you get sheaves. So notice that logically speaking, we started from sheaves and came to stalks, and then we talked about sheafification, so as to make sure that we do not run into trouble like we ran right here. But in practice, I think it helps to just think in terms of stalks. In particular, when we talk about sheaves like this, O of D, these are nothing but a set of points. So we will attach multiplicity to every point, but that basically means we have to start thinking in terms of points. So the moral of the lecture was, think in terms of stalks, because stalks are very concrete. You are just talking about a point P, not some sets U and V which continuously vary.